We examine ethanol now as a really important molecule in chemistry. Remember, here's the ethanol molecule represented on the lower right with a molecular model kit, or on the left as a structural formula. Note that we're really going to examine ethanol as a source of ethylene. A couple of things to notice about its structure. It has a functional group, the hydroxy. It has an alkyl group, the methyl tail. If you'd like to think of this as a head and a tail, the hydroxide group at one end acts like a polar head, and the alkyl methyl group at the other end acts like a non-reactive non-polar tail. Now, ethanol happens to be soluble, meaning that it can be dissolved in water. But why is this so, considering the nature of its non-polar alkyl tail? Well, there's two reasons. It's a very small molecule. The smaller a molecule is, the more likely it is to dissolve in any solvent. For example, molecular iodine does have a partial solubility in water, even though water is polar while iodine is non-polar. Here we have a very small molecule, so the smaller it is, the more likely it is to dissolve. Secondly, it has a polar hydroxide head, meaning that that area of polarity on one end of the molecule is strongly attracted to the polar solvent water, which means that it is able to be dissolved by water molecules. Now, ethanol itself acts as a very important solvent. If you think about it, according to what I've just said, a polar head and an unreactive tail mean that it's actually capable of doing both. When I say doing both, of dissolving both polar and non-polar solutes. Let's think about it. The presence of the hydroxide group at the head, for example, means that one end of the ethanol molecule is polar. Why? Well, the oxygen is incredibly electronegative, so it unevenly shares the electrons with both the carbon and the hydrogen that it's attached to. So the polar end of ethanol means that it can dissolve polar substances, because like dissolves like. There's a representation of the polarity. A zoom in, you have a relative positive charge on the hydrogen and the carbon, and a relative negative on the centralized oxygen. Ethanol's alkyl group, however, the tail, the methyl end of the ethanol molecule, is nonpolar. So that means that that end of the molecule is capable of dissolving non-polar substances, because also like dissolves like. So substances with weak dispersion forces, this end of the ethanol molecule has an attraction and an affinity for those particular substances. So it's this end of the molecule that gets to work, so to speak, when dissolving non-polar solutes. For example, this end here, you can see there that that's an end hanging off of the ethanol head, is able to get involved in non-polar miscibility and dissolving. So it's a multi-purpose solvent. It's miscible in water and pentane. That means it can dissolve in, mix throughout, a solution that is polar, water, and one that is non-polar, like pentane. It can form hydrogen bonds with other substances and therefore dissolve them. And its alkyl group, being non-polar, is able to dissolve the non-polar substances. This, for example, happens when the non-polar tail forms dispersion forces with non-polar substances, such as molecular iodine. Therefore, ethanol will dissolve in substances like heptene, which is a non-polar hydrocarbon. Now, ethanol is a very important source of ethylene, and this is of incredible importance to us in the HSC Chemistry syllabus. The way that we can use it as a source of ethylene is to dehydrate it. You know the process of dehydration. If you're dehydrated, you are lacking water. So if we cause the ethanol molecule to lose some water, by removing two H's and an O, we will move the ethanol molecule into a molecule of ethene. The way that this is achieved is to gently warm ethanol in the presence of concentrated sulfuric acid. It will then lose that H2O molecule. So here's a representation. Ethanol, in the presence of concentrated sulfuric acid and some gentle heating, will yield ethylene and water. We have dehydrated the ethanol by removing a water molecule. Now, this is a reversible reaction where we can actually rehydrate or simply hydrate ethylene to ethanol. Now this is done by using dilute sulfuric acid as the catalyst and some gentle heating. So therefore we can move back the opposite direction. Now this relationship is of incredible importance to you in Year 12. The way I remember whether it's concentrated or dilute is to think about what's happening behind the scenes. Let me explain that. If I have a dilute concentration of something, it means that I've got a lot of water there, don't I? So if I have very dilute juice, it's been watered down so that the end product is very watery. That's the same here, that's how I remember it. If I want to form a hydrated substance, ethanol is the hydrated form of ethylene, I need dilute H2SO4 because my end product is watered down. It's like watered down ethylene. If I want to dehydrate ethanol to ethene, then I need a concentrated solution of sulfuric acid where we don't have much water, because in the end I would like to remove the water. So that's how I remember whether it's concentrated or dilute H2SO4. You need to know that process of dehydration and hydration of ethanol and ethylene, so get it into your notes, make a palm card or a poster, whatever you like. So the process of dehydration and hydration is applicable to many substances. You can do the same, say, for propanol. You could dehydrate that to propene, or hexene, for example, could be rehydrated to hexanol in the same way that we've just examined. These questions are now of vital importance for you. Have a go at them in your textbook and check your answers from the back. The other thing we need to know about ethanol is that we can source it from biomass, in other words, from the organic biomass around us, plant matter. It's a viable source of ethylene, which means it can come from a renewable source. Remember, currently, ethanol tends to be hydrated from ethylene that's sourced from crude oil. But we could do a different procedure which would enable us to get ethanol from biomass. But how can we do that? It's via a process called fermentation. Fermentation will now be examined as a renewable process for sourcing ethanol from biomass. So let's have a look at it. Today, fermentation only accounts for a very small percentage of industrial ethanol. At the moment, nearly all the ethanol that we use in industry as a solvent and a fuel comes from the hydration of crude oil-derived ethylene. So at the moment, this isn't a massive procedure simply because of the cost. But in the beverage industry, all of the ethanol you find in alcoholic drinks has come from fermentation. And this has been around for thousands of years. Human beings have been fermenting sugars for thousands of years to produce alcoholic beverages. But as crude oil starts to run out, ethanol from fermentation of biomass is going to be a very important industrial process to both provide us with that industrial solvent, ethanol, and a fuel source. But what is fermentation? Well, it's the process by which glucose is broken down into ethanol and carbon dioxide by the action of enzymes in yeast. And the way that it is examined in the chemistry course is to acknowledge that from an environmental point of view, it's an intriguing source of ethanol because biomass is renewable. And within biomass, we have readily available glucose in the form of starch or cellulose. Remember, cellulose is a condensation polymer of glucose, and we can reverse that polymer and break it back down into the monomer units of glucose using cellulose or a strong acid. So once we've extracted the glucose monomers from cellulose, which is found in all plants, we've got the starting point of fermentation. So let's examine what we do then. We get a solution of glucose and prepare it. We add some yeast to it at a defined temperature of 15 to 35 degrees C. Now the yeast colony loves the glucose and begins to multiply in number, producing enzymes which go ahead and cause the glucose to be further broken down into ethanol and carbon dioxide. The carbon dioxide is produced as a gas, ethanol is aqueous. However, with this process of fermentation, we can only get to a concentration of about 15% ethanol before the conditions become too harsh for the yeast to continue to survive, and they actually die at around about 15-16% concentration ethanol. Now this isn't a very high concentration, so we need to then distill the leftover solution in order to purify our ethanol to 100%. Remember, how do we separate two liquids? Well, if they have different boiling points, you can do it via distillation, which we have done. Ethanol boiling at about 78 degrees will be the first fraction off, and we can pick up 100% ethanol by further refining and distilling. Now there's the equation that you must know, Year 12. 1 mole of glucose in the presence of yeast becomes 2 moles of ethanol and 2 moles of carbon dioxide gas. Note the states, they're very important. Well, the beauty of fermentation as a process to produce ethanol is that all biomass contains cellulose, and many plant products actually contain glucose in the form of starch, which is a much more soluble form of glucose than cellulose, so the step of breaking apart the polymer of cellulose can be skipped if you have a very starchy starting product. For example, cornstarch, which is used in Brazil as the starting point for ethanol, enables the Brazilians to skip the step of breaking apart cellulose, which is costly and time consuming, and they can simply form a solution of cornstarch in the presence of yeast, which will then go and ferment. Sugarcane, fruits and other plant types also provide really good starting points for fermentation due to the readily available sugars and glucose in their structure. So ethanol is an excellent fuel because it yields 1360 kilojoules per mole of energy. That's a positive for ethanol. But even more positive than that is that it burns very cleanly. There's only 2 moles of carbon dioxide for every 1 mole of fuel burnt. If you think about an octane-based fuel, you get 8 moles of carbon dioxide for every 1 mole of octane burnt. So it's a clean burning flame. There's a representation of that combustion of ethanol. Likewise, you would need to be able to reproduce a combustion of ethanol to show fuel, to show the oxygen consumed, the carbon dioxide produced, and the amount of energy released as an exothermic reaction. The other good thing about ethanol is it can be used as a fuel extender. At the moment, with our dependence on fossil fuel-derived hydrocarbons for fuel, we can extend those by adding a mix of 1 in 5 ethanol up to 20% without any harm to existing engines in cars. Now that's a really, really good way of prolonging the life of the finite fossil fuels that we currently depend on by using ethanol as an extender. Now it's easily transportable, and of course it's renewable. The negatives surrounding ethanol is that while it yields 1360 kilojoules per mole, that's a fair bit lower than current crude oil-based fuels. So it yields good energy, but not as much per mole, so we need to use more of it when we're using it as a fuel source. The other problem is that, and this is the major problem, we need large land areas to grow the biomass that's going to be used as a basis to source the ethylene and then ethanol from. This is going to mean that we have increased deforestation. We have associated cropping issues such as salinity, erosion, fertilizer runoff to producing eutrophication, which is the increased phosphates and nitrate concentration in waterways, which increases the likelihood of algal blooms. And there are ethical problems. At the moment, much of the world is classified as poverty-stricken or in fact starving, and so we have an ethical dilemma. Should we be using arable land for crops for fuel, or should we use that arable land for crops for food? And so there's an ethical drama. What is more important? Of course, feeding the masses with that vital need of food is far more important than our fuel needs, but the West is driving the global economy, and if we need an alternative to fossil fuels, there will be ethical debates that rage in the near future. The other issue is the waste of fermentation. After all is said and done and the 15% ethanol is distilled off, there's a lot of waste left over. In fact, 85% of that is going to be a waste product. Now, some of that liquid could be recycled and re-fermented, but there'll be a lot of husk and fermented biomass left over that needs to be disposed of. And if you're used to driving past Cassegrain Winery at certain times of the week and day when they are fermenting, there's that very strong pungent smell that's an environmentally damaging leftover waste product of fermentation. And so there's going to be an increasing demand for an adequate disposal of this fairly pungent waste product of fermentation. Here's a good schematic representation of why ethanol can be regarded as a renewable fuel. If we start on the left of screen, we have the process of photosynthesis, whereby sunlight combines with carbon dioxide and water to produce biomass, which is essentially a polymer of glucose at the top. Now there's energy input during that. If we're going to do this via cropping, in the red circle, you need energy, which of course comes from fossil fuels at the moment, into this cycle. Glucose then can be found in the form of sucrose or starch or cellulose, which can be fermented into aqueous ethanol. However, at this point we need some more energy to come in to distill that and purify it to 100% pure ethanol down the bottom of the circle. So we've got another energy input, and the energy for distillation of course is going to come from the power grid, which at the moment is sourced from crude oil derived fuels. And then that pure ethanol can be used for all manner of things, combustion in cars, etc. But the combustion of the pure ethanol is going to release carbon dioxide and water back into the atmosphere, which can recombine with sunlight and be fixed back into glucose via photosynthesis, and so round and round it goes. The important thing to notice here is that we've got energy coming in and energy coming out, and it's a renewable cycle where we're accounting for everything that goes in and everything that comes out, with the addition of the energy requirements for the cultivation of crops, top left, and the purification of ethanol via distillation, bottom right. A nice overall schematic representation of ethanol. What we're going to see here is that we can refer to ethanol as carbon neutral when we combust it. Have a look at these equations to represent it. Photosynthesis is an equation you must memorize. 6 moles of carbon dioxide are used in photosynthesis. During fermentation, for every 1 mole of glucose that was produced in photosynthesis, 2 moles of carbon dioxide are released. Likewise, when we go and combust the ethanol that's produced from fermentation, 4 moles of carbon dioxide are released. So if you take the 6 moles of carbon dioxide that are consumed in photosynthesis and add them to the 6 moles that are ultimately produced in fermentation and combustion, we can see that ethanol is carbon neutral with regards to these 3 processes. One of them consuming 6 moles and the other 2 re-releasing those 6 moles. So carbon neutrality is really, really important when we speak about the environmental impact of an alternative fuel. The only problem here is that it doesn't show the energy that was required to allow fermentation to then be distilled into pure ethanol, and the energy that was used to grow the crops to give us the biomass for the fermentation process. So while it is photosynthesized, fermented and combusted in a carbon neutral setting, at the moment we still need extra energy to go into that system, and that extra energy is also going to emit carbon. But the processes I just spoke about are now mentioned on the screen. So overall, the current production of ethanol still relies on fossil fuels, because those 2 energy inputs for crop cultivation and distillation are coming from the power grid, which is driven by fossil fuels. Well, ethanol in Australia at the moment, if you have a look, the production costs way more for ethanol than petroleum, so we're currently using blends. And car manufacturers agree at the moment that a 10% ethanol mix does not damage car engines. It's likely that you could get away with far more than this, but at the moment the culture in Australia is one of hesitancy for ethanol. Greater than 10% apparently can potentially harm engines, but there's good science to suggest that this is not the case, and it's just a way for the oil companies to keep people reliant on fossil fuels for the moment. The other thing that's interesting is that there's no conclusive studies at the moment to show that ethanol produced from renewable biomass releases any less carbon dioxide than current crude oil-based petroleum, based on the fact that there's those other 2 energy inputs. Well, there's ethanol as a fuel, but now let's just quickly examine ethanol as an alkanol, another class of hydrocarbons. So ethanols belong to a group of alcohols known as alkanols. Why? Well, they have an alkane section and an OH group. One of the H's was replaced by an OH, and so we refer to it as an alkanol. Now have a look at how we name alkanols. There's an alkane, CH4, belongs to the homologous series of saturated alkane hydrocarbons. An alkanol, you replace the H with an OH, so it's CH3OH. You name it methanol. Here is ethane. Ethane has an easy translation into ethanol when we replace an H with an OH, and so we call it ethanol. Here's another one, octane. There's the molecular formula for the related alkanol, so you name it octanol. Very straightforward. You're simply replacing the suffix ane with an ol. To name an alkanol, this comes from your textbook, you simply delete the E of the alkane and add ol. Methane, methanol, ethane, ethanol, propane, propanol, and so forth. You also add a number prefix, that's a number before it, to show the position of the alcohol group. We do this in the same way that was used for the position of a double bond. Now no number is needed for methanol or ethanol, that's because you can only ever put it on carbon 1. So for example, if you had a hexane and you changed it to hexanol and the hydroxide was on the third carbon, you would call that 3-hexanol. Very, very straightforward. Worksheet 5 of Conquering Chemistry Blackline Masters is very appropriate at this point. You need to get that done. The last thing is to look at ethanol's molar heat of combustion. Can you remember what that is? Well, it's the amount of heat liberated when 1 mole of a substance is completely combusted with enough oxygen at standard temperature and pressure. So delta H is negative because no heat was absorbed, it was actually released, so there's a negative need for the heat. Delta H for all combustion is negative, exothermic. You need to get used to seeing the molar heat of combustion for ethanol listed like this. Ethanol, in the presence of oxygen, releases 2 moles of carbon dioxide, 3 moles of water, and delta H is negative 1360 kilojoules per mole. Now this is going to be the basis of your first assessment task, where we're going to compare the molar heats of combustion of a few alkanols. There's an example from your text of a typical setup. If you turn to page 36 and 37, follow the example as we calculate delta H for ethanol using this apparatus. When you do your pracs, you'll find that you can do worksheet 7, and you can now also complete worksheet 6 from Conquering Chemistry Blackline Masters. The questions on page 38 of your text are very helpful at this point. Work through all that now, check your Blackline Master worksheet answers on Moodle, and make sure you're up to speed with ethanol as a solvent and as a fuel source, and that you can make sense of molar heats of combustion.